Hi class, today we'll discuss section 6.3, finding probability using a normal distribution. Recall, for any normal distribution or distribution that is approximately normal, the area under the curve for any region is equivalent to the probability of the random variable falling within that given region. In the previous sections, we reminded ourselves how to convert x values to z values using our standard score, z equals x minus mu over sigma. If we do some simple algebra, we can resolve the formula for the value x to get the following. X equals z times sigma plus mu. We just multiply each side by sigma, and then we add mu by properties of equality. We will focus on this formula in the next section. Given any normal distribution, we call an x distribution, we have a formula allowing us to translate values from the x distribution to our standard normal distribution. We call the z distribution. We can also translate values from our z distribution back to our original x distribution. So if we're given a population and a continuous random variable x that's normally distributed, we can convert these values to our z distribution, and we can convert back if needed using the following formulas. The idea here is that the area under the curve for any region in our x distribution is equal to the area under the curve for the associated region in our z distribution. Again, if we have an x distribution and we look at an area, then when we convert it using our standard score, remember, our value, our data value minus our mean divided by sigma. So we convert our value A, we convert our value B. These areas are equal. Let's look at an example. Dairy Delight Farms has been milking cows for many generations. They have calculated that on average, the milk production per dairy cow over a month's time is 1,931 pounds, with a standard deviation of 67.1 pounds. The manager has noticed that the milk production from their cows seems to have been slowly decreasing in the past couple of years. However, their sales remain steady. Determine the probability that a random cow chosen from the farm produces less than 1,831 pounds of milk per month. And we will assume that the milk production from the cows is normally distributed. Now, we are in a position here to use the normal curve to answer this question, since we are told to assume that milk production data are normally distributed. And we are given the mean and standard deviation of this distribution. We first need to define our continuous random variable x so that we can write our desired probability. We always define x to be the measurement that is normally distributed. In this case, for this problem, x is the milk production from a cow on Dairy Delight Farms, and this is given in pounds. Using this notation, we are interested in calculating the probability that x is less than 1,831 pounds. We can draw this probability on a normal curve. This is our x distribution with mean 1,931, and so it's going to be a little below the mean. And remember that probability in this case, since it's less than, it's going to be a probability to the left. We notice that in this case, again, we are interested in an area to the left of 1,831. In order to use our cumulative probability tables, we must convert the value x equals 1,831 to a z value first. We remember that the problem states mu is 1,931 and sigma is 67.1. Using our standard score, we get z is approximately negative 1.49. And remember that we always round our z values to 2 decimals. And this is because our tables use 2 decimal places. Looking up z equals negative 1.49 in table A, we see that the shaded region has an area of 0.0681. Remember that the area to the left is found directly using table A or B. We can also use our calculator to compute this area directly. Let's recall that we are given an X distribution, which represents the pounds of milk produced per month, with mean 1,931 and standard deviation 67.1. We are interested in finding the probability that a random cow chosen produces less than 1,831 pounds of milk per month. We can write this as follows. This represents the area to the left of the value 1,831. To use our calculator to compute this directly without using statistical tables A or B, we first press second and our vars button, which is a little below the stat. It's diagonal from our stat button that we're used to pressing. So press second and vars. We then we make sure that it's highlighted over the TI distribution, TI distur, meaning TI distributions, and we select the normal CDF. Now there's a normal PDF, don't choose that one, but right below it is our normal CDF. We input the following into our command function. We put our lower bound, our upper bound, our mean, mu, and our sigma as shown below. Now, a question here is, what is our lower bound? Note, we will use the following lower and upper bounds for certain areas. If it's an area to the left, our lower bound will be -1 times 10 to the 99th. If it's an area to the right, our upper bound will be 1 times 10 to the 99th. Now remember what this does. This is our scientific notation that you may recall from high school class. This takes our decimal number and moves it 99 places. So this is, a very large negative number, so it's a very small number. And this is a very large positive number, so it's a very large number. Now, to write this in our calculator, we will use the scientific notation feature by pressing second and our comma button here. Right, this is second plus our comma button. So remember that our comma button is below our sign button here. So second, comma. Our calculator represents the times 10 portion as E. So we will write -1 E99 to represent -1 times 10 to the 99th. So again, what we do is we click -1, and then we're going to click second, comma. This is going to give our scientific notation, and then we're going to click 99. And it should look as follows. So this is an area to the left, so we use it as a lower bound. -1 E99, that's our lower bound, comma, we're going to go up to 1,831. Our mu is 1,931, and our sigma is 67.1. And we can see that from this picture. Notice I'm taking a very far number here, -1 with 99 zeros after it, as my lower bound, and I'm traveling up and I'm ending my upper bound at this value. And I'm using my mu and my sigma in my calculator computation. Now, if you don't like that method, we can utilize our statistical tables A and B as we did in section 6.2, but everyone should know how to use both. It's just when it comes to the test, use the method that you feel most comfortable with.